Hey everyone, this is Tej Patel here. Just want to introduce myself. This will be part of the 2020 virtual anodizing conference. The presentation you're going to have today is going to be about anodizing seal additives. I'm a director at Techevon, and I'll be doing this presentation with one of our R&D engineers, Archana.
Hi, my name is Archana Sonejee, and I'll be working with Tej on this presentation today. So let's begin, Tej.
All right, so today's presentation is going to cover a few things. The overview of sealing, some of the key factors that you need to consider as an anodizer as it relates to that, the types of sealing, hot nickel, mid-temp, non-nickel, the types of additives that play factors into all those types of sealing, the importance of those additives as it relates to seal quality, so light fastness, passing, blue dye stain tests, corrosion resistance, you name it. And then the benefits of correct sealing on light fastness. Now, with all that said, even with going through that discussion, there's still going to be aspects where anodizers battle sealing issues, and we'll touch on that at the end of the presentation. All right, so just kind of a summary. The sealing of the anodic coating is one of the most critical steps next to the anodizing, because what it's designed to do is ensure that that product that has now been anodized will hold up in the field. So it's a vital part of the process. And after all of the labor and costs that have been put into this part, this one step, if not done correctly, can be kind of catastrophic. So there's several key factors that play a role in seal effectiveness. The anodic coating density and thickness. The denser the coating, the more easily it lends itself to sealing. The thicker the coating, the longer it takes to seal. Temperature. Usually the higher the temperature of the bath, the faster the sealing and the hydration process occurs. The same applies for the pH. If you have a high pH, you seal much faster, but you run the risk of sealing smut. And that's kind of the interplay here that we're always battling is sealing and getting a good seal, but not having the smut associated with a good seal. And then the final two components are the active ingredient of the seal, in this case, maybe nickel, and then the seal additive chemistry. So, and I'll touch on this later on in the presentation, with that hot nickel or that mid-temp nickel seal, you're going to be getting an additive or a surfactant. So the amount of that surfactant, the type of that surfactant, all plays a role in this. The different kinds of sealing that we're going to kind of mention here, hot DI, which is your traditional hot water sealing with no nickel, a hot nickel done at above boiling or boiling, a mid-temp nickel, which is done between 170, 180, a cold or room temp sealing, dichromate sealing, which isn't as common anymore, and then NickelFree Sealing. So to kind of move right into it here, when we talk about seal additives, if they aren't managed correctly, there are a few things that you need to look for. One, sealing smut. Two, dye bleed. Water staining. Seal test failure. And then finally, yellowing. And yellowing is a phenomenon that occurs when a part is put in an outdoor exposure scenario, and through UV light and heat, that surfactant yellows up. All right, so the anodic sealing process is essentially two steps at its most fundamental level. One, you are filling that porous oxide layer with an active ingredient, in this case, nickel for most sealing processes. And then that step is followed by a hydration step. So you'll see in the image here, your porous coating, kind of looked at from a cross-section perspective. That pore is filled with, in this case, nickel, and then hydrated. Now, during that hydration process, you're taking aluminum oxide and water, and you are essentially hydrating the coating by creating a hydrous phenomena, which is the Al2O3 with the 3H2O. So and by doing so, you're pinching those pores shut. So it's kind of a curing of the anodic coating in a way. Now, the whole objective of the sealing process is to do a number of things. One, improve the corrosion resistance. So if this is a part that's used in a marine application, you want to mitigate any sort of corrosion that could occur. Preserve color. So if it's a dyed part, and this part's put into the field, you want to ensure that that color is preserved, it doesn't fade or lose color over time. Improve lubricity. So in many automotive applications, lubricity plays a vital role, for example, for sunroof tracks. And that lubricity comes from a specific surfactant used in your nickel seal. And then improve dielectric resistance. So as I mentioned earlier, the sealing step is vital for a number of reasons, and that just hints to some of it. And as we go through this process, we'll understand there's kind of an interplay here playing between how we get as much nickel in the coating as possible, but also hydrating it at the same time, because you need both elements in order to ensure a good seal. You need some sort of UV filter, in this case nickel, but that needs to correlate with or be accompanied by a hydration step. All right, so the table here is kind of a summary of the most common types of seals, and I've hinted on this a little bit. So we'll go into each one with varying degrees of depth, but this kind of will give us an overview of what all is out there. So hot water sealing, essentially this is just DI water at a boiling temperature where you'll immerse the part into this solution. And what it does is there's no nickel incorporation. It's literally you're just hydrating the pore and pinching those pores shut through hydration. Now, some of this hot water type of sealing, you can use additives to manage the smut, because usually when the immersion times in a bath like this exceed 3 to 4 minutes, as you hydrate, you create smut. And so many anodizers will use an additive to offset that. Hot nickel sealing. This uses a nickel salt. In most cases, it's nickel acetate in a boiling solution with some sort of surfactant. But the intent here is you want to hydrate the pore, and while you're hydrating that pore, you want to allow nickel through a concentration gradient to go into that pore. Now, the difference between the hot nickel and the mid-temp nickel is the hot nickel obviously occurs at a much higher temperature. The mid-temp nickel allows you to have nickel incorporation of the coating, but also gives you an element of lubricity, which is linked to the different type of surfactant that's used in that coating. So in general, mid-temp nickel is very popular. It's done at a lower temperature, so it saves on energy costs, and it gives you a sense of lubricity that you won't get with a hot nickel seal. So it's become very popular in the industry of late. Cold seal / room temp seal. So essentially, cold is a relative term, but the intent of this seal is to be done at a room temp temperature of at least 85 degrees. So obviously in winter, you may have to incorporate heaters into that seal, but as a rule, it's done at a much lower temperature than its counterparts of mid-temp and hot nickel. But the logic is the same, is we're trying to incorporate nickel into the anodic coating, but in the case of a cold seal, we're doing that in 2 separate steps. The first step will be the cold seal step, where we're using a nickel salt with fluoride to go into the anodic pore. That step is followed by a hydration step, which is essentially the hot water sealing that you're seeing at the top of this chart. Duplex seal and dichromate sealing. This is a pretty old type of seal that was used in the past, and what it involves is taking an anodized part, going into a dichromate bath, followed by a nickel acetate bath, and the result is a part that looks green. And when this seal was more commonly used, the quality of that seal was assessed on how green the part was. So a green part indicated a good seal. In the current environment, dichromate sealing isn't very popular. It's on a few specs, very rarely used. The most common type of sealing you're going to see is nickel sealing. High alkaline resistant sealing. So this is something that's become much popular of late, and it involves a nickel salt type of seal with a second step, which can vary in proprietary chemistry. But the intent here is to create a seal that can hold up to a 13 or a 13.5 pH. And originally, it was developed for touchless car washes to prevent a high alkaline environment where the anodic coating was being damaged. So the intent of this seal is to ensure you're going to withstand those types of high alkaline scenarios. Now, that same technology has been used and applied in the medical industry and also in the cookware industry. So it's becoming a lot more popular of late and gaining more traction in applications for industrial uses. Then the final process is NickelFree Sealing. And what this is similar to your mid-temp nickel sealing. However, the primary difference is the active ingredient is not nickel, it's a different metal. This has become very popular for electrolytic sealing. Nickel discharge can obviously be costly and somewhat challenging if you have environmental regulations. So many customers who are doing clear or electrolytic coloring will use a non-nickel seal to seal their parts and ensure that they're still getting good quality as it relates to light fastness, but don't have to deal with the environmental issues associated with nickel. All right, so for each one of the seals we discussed, all of them has a complementary additive. And this table will kind of go through what those complementary additives are, the importance they play, and how they improve your overall seal quality. So in the case of hot water sealing, as I mentioned before, when you're taking an anodized part and you put it into a hot DI bath of water, after it's in there for more than 3 or 4 minutes, you start getting sealing smut. And smut isn't a bad thing. It indicates to you that you're actually getting the hydration of the pore, but optically and cosmetically, it doesn't look good. So what many individuals do with hot water sealing is they use a poison to hydration or a additive that stops hydration to prevent that smut from forming. Now, the trade-off there is in doing so, you may not get a good seal, but you will get a reduction in smut. And I'll go into that further on subsequent slides. Hot nickel sealing and mid-temp sealing. Both of these types of sealing require a surfactant. And the surfactant is used to help obviously reduce surface tension and try to lend itself to getting as much nickel in that coating as possible. The challenges with these surfactants are twofold. One, over time and through heat, they break down. And in the case of the hot nickel, when that breaks down, there's a risk of residue building up on the part. In the case of the mid-temp, the surfactant life is a little bit longer, and so mid-temps become a little bit popular because of the fact that you can seal and get a good quality seal with a much shorter immersion time than you would with hot nickel, and the surfactant can hold up to temperatures that are lower, in this case 170 degrees. But the battle you will always be fighting with these two types of sealing is managing that surfactant, and if it is being depleted disproportionately, how do you incorporate that surfactant into the chemistry to ensure you're getting parts that don't have smut on them? Cold seal and room temp sealing. So the primary additive here is a fluoride additive, and the fluoride is used to transport that nickel from the cold seal solution into the pore. If fluoride isn't managed correctly, you won't get enough nickel in the pore, and you likely won't pass blue dye stain testing. So it's a scenario where this type of chemistry is extremely popular because it lends itself to not having to use any sort of surfactants. So there's no risk of consuming or breaking down a surfactant disproportionately. And what can be a challenge with the cold seal as a counter, though, is if an aluminum part is dropped into that bath, or there's something that consumes the fluoride, you will have to ensure you measure that to make sure it's in line. But as a rule, managing the fluoride is much easier than dealing with the surfactants associated with mid-temp and hot nickel. High alkaline resistance. So the primary step in this starts with a cold seal. So there's obviously the fluoride additive that's important. And then in the second step, there's a proprietary additive that's used. It depends on, certain companies provide different additives, but essentially there's a second step additive that you can use to ensure that you're getting the right second step to meet this 13.5 pH requirement. And then the final sealing method, NickelFree Sealing. Again, this uses a surfactant to control smut, much like the mid-temp surfactant. And again, you'll fight the same battles you're fighting with any surfactant-based sealing. Is over time it breaks down, and as it breaks down, you run the risk of losing seal quality. All right. So the next slides that we're going to touch on will basically be kind of deep dives on each type of sealing, some potential pictures that show what can happen if additives are not managed correctly, along with an ADT, which is an acid dissolution test. And essentially what that test is telling us is a part that is sealed is put into a chrome phos bath for a certain amount of time. The weight is measured before and after that immersion. And the less weight that is lost, the better the seal. And essentially what that means is if the seal is good, less of the anodic coating will be destroyed in that bath. So what you're looking for is kind of like a golf score, a low number. So let's start off here with the hot water sealing. So you'll see two panels there. there is one panel which is dyed black that has no hot water additive, and another part of the panel that's dyed gray, which does have a hot water additive. And you can see there's a pretty significant white kind of water stain on the part on the left. And so what happens with boiling DI baths, after a part has been immersed in there for more than 4 to 5 minutes, you start getting hydration throughout the anodic pore all the way up to the surface. And so in doing, the surface hydration is what shows the majority of the smut. So what many chemistries try to do to mitigate this is they stop hydration. Now the risk you run by stopping hydration is you're not going to hydrate the pore, and your pore, because of that, may be susceptible to poor seal quality. Certain additives only suppress hydration at the surface, which means the pore itself is hydrated and fully and has its full integrity, whereas the surface where you see the smut does not. So in situations like that, when you use the correct additive, you will actually get very good seal quality, but not have the smut associated with hydration. So it's almost like a targeted additive that only affects a portion of that anodic coating. So what you'll see here in the ADT values are the part on the left, before we made an additive addition, had a much higher ADT value than after the additive. It dropped significantly. So there are ways to get good ADTs and use a hot water seal. Some additives are much better than others because they have a targeted approach in how they handle hydration. But that's something to consider when you're doing hot water sealing. You know you have to immerse a part in a bath for more than 5 minutes. You're going to need some sort of additive to ensure you don't smut up. All right. This slide, it discusses hot nickel sealing. And so what you'll see here again is another image where you have a part that is sealed in a hot nickel bath that doesn't have enough of the surfactant or seal additive. And the part on the right is a similar panel that has been immersed in that same bath. However, an addition of the correct surfactant has been made. So what you'll see is that iridescence associated with the no seal additive part is a phenomenon wherein you're incorporating nickel into the coating and you're trying to hydrate it, and it reflects light and results in iridescence. And so that's usually an indicator of, yes, I have sealed the part, but I clearly do not have enough of the appropriate additive chemistry to manage the cosmetic look of it. So the battle you're with the hot nickel seal is twofold. One, you're trying to incorporate nickel into the coating, but also hydrate and pinch those pores shut. So imagine yourself trying to fill a pore with nickel with the pore itself shutting at the same time you're trying to do it. So the issue with hot nickel and even mid-temp nickel is you're not able to optimize the amount of nickel that gets into the pore, and as a result, you could potentially not have as strong of a seal compared to other types of seal chemistry that do allow those two steps to occur in individual tanks. Now, the benefit of the surfactant is it reduces the surface tension and allows that nickel to go into the pore. But again, if that seal additive is not managed correctly, you won't get a good ADT. So if you look at the ADT values, clearly before the additive, you were at 13.7. Now that's already an improvement from what you were seeing with the hot DI in the slide earlier. So there is a benefit in just using nickel itself. You're getting some nickel into the pore at minimum, but closing and performing that hydration step is critical. And so after you have the seal, after you make the addition of the seal additive, which allows more nickel to get into the pore and allows you to fully hydrate that pore, you'll see that your ADT values are much lower. So again, the big takeaway here is the surfactant management is absolutely critical. And one of the indicators I like to look at to know if I have enough surfactant in that bath is a water break test. And the same logic will apply on the mid-temp seal when we go there. But that's usually an indicator of if we have enough of the appropriate chemistry proportions, a water break is a good metric for that. All right, mid-temp nickel sealing. So we kind of hinted on this earlier. There's a battle that you're fighting between hydration and nickel incorporation. And the difference with a mid-temp seal compared to a hot nickel is twofold. One, it's being done at a much lower temperature, 180 degrees, and the type of surfactant that is being used is different. And for those two differences, mid-temp sealing has become a lot more popular. It's generally faster than your hot nickel seal, and it results in much less smut than your hot nickel seals would. It still runs the same pitfalls and risks that a hot nickel would, in that they're over time, and it may be over a longer period of time, you will burn off that surfactant and you'll have to manage it. But in terms of improving overall production efficiency and not having to wipe parts, it's become a lot more popular of late. Now you'll see in the images in the left here, we've done a blue dye stain test. This is a clear part. The blue dye stain test, we'll talk a little bit more about what that entails, but essentially you're putting nitric acid on a part, following up by a blue dye. And if that blue dye takes, that means your seal did not withstand the nitric acid attack, and the blue dye actually dyed the anodic pore. So what you'll see here again is a phenomenon wherein there wasn't enough of that seal additive or that surfactant. The part failed blue dye stain. An addition was made of that surfactant, and now you've passed blue dye stain. And the critical thing here is a lot of customers will dump their baths the minute this happens and they fail a blue dye stain, wherein it could be something as simple as just making an additive addition. So keep that in mind when you're assessing your sealing chemistry. Just because you had a failure by a blue dye stain test or even an ADT doesn't necessarily mean you need to dump the whole bath. There are ways to salvage that bath without dumping it and saving yourself the pain of dealing with the nickel discharge. So what you'll see here again is when we did our ADT values, you'll see the 11.7 milligrams per square inch is an improvement compared to the hot nickel of 13. So again, this is why the mid-temp nickel sealing is much more popular. You are getting a faster sealing, even though the surfactant is a challenge to manage. Now, when you make that surfactant addition, you'll see the huge drop in the ADT value to 0.38. So again, the critical element here is managing that seal additive, and by doing so, you optimize that trade-off between nickel incorporation and hydration. All right, now on to cold sealing. So the cold sealing is very different than the sealing we've discussed in the last two slides. The goal of cold sealing is to essentially create a conversion coating that's formed when you have fluoride in a bath. And what the fluoride does is it creates a nickel aluminum fluoride complex that plugs that anodic pore. So we're not filling it with nickel like we were in the other steps, we're filling it with a nickel aluminum fluoride complex. And by doing so, and by using fluoride as the vehicle to incorporate nickel, not just a concentration gradient, we're able to get 4 times more nickel into the coating compared to traditional high temp and mid temp nickel seals. So what that means is the battle that you're fighting between hydration and nickel incorporation isn't one you'll be fighting with a cold seal, because the cold seal bath in that first step is designed to do one thing and one thing only, and that is pump that coating full of nickel and as much as possible. And in doing so, you build a very robust anodic pore that is not hydrated, but filled to the brim with nickel. Now, because of that, there is a second step associated with cold sealing, and it is a hydration step. And that hydration step is essentially a hot DI or hot water dip, ranging from anywhere from 5 to 7 minutes. It depends on the type of part, the type of alloy, but it's a dip of at least 5 minutes. Now, when you've followed up a cold seal with that hot dip, you've essentially achieved what a mid-temp and hot nickel seal try to do in one tank in 10 to 15 to 20 minutes. So the resulting phenomenon here is a process that is much more robust, incorporates tremendously large amount of nickel, and gives you a process that is much more reliable in terms of heat consumption from heating the tank. Now, if you look in the pictures here, the fluoride, as I mentioned, is a key element to this. And if you don't manage the fluoride correctly, one of two things can happen. If there's not enough fluoride, you won't get a good seal and a poor ADT value. If you put too much fluoride in there, you'll get an over-sealing phenomenon and you'll see iridescence. And that's what the slide on the left, on the image on the left shows, is that iridescence associated with excess fluoride or an immersion time that's too long, 20, 30 minutes. Because remember, with the cold seal, you don't need to seal for longer than 7 minutes at most in certain cases. Now, depending on what the application is, maybe you go up to 10 or 15, but you don't need long immersion times like you do with the hot nickel and the mid-temp nickel. So if you are getting iridescence, that's usually a result of over sealing, which could mean you have too much fluoride, or you're immersing the part in that bath longer than it needs to be immersed. Now, if you look at the ADT values, the values prior to adding the additive and once the additive is added, you'll see significantly lower numbers than what you've seen in the previous two slides. Before the additive, you're already at 2.86 milligrams per square inch, but then after you make that additive addition of the fluoride, you'll see that your ADT value drops precipitously. So again, just like your hot nickel and mid-temp nickel, there is a seal additive to manage. The difference with the fluoride additive is it won't burn off disproportionately the same way a surfactant would. So the only way that your fluoride kind of gets disproportionately consumed could happen when you have dropped a part in your cold seal bath, and that part will sit there for weeks and slowly consume that fluoride. But as a rule, as long as you manage that nickel chemistry and you're making regular additions, the maintenance of a cold seal bath isn't any more difficult than your normal mid-temp or high temp. In fact, it may be easier once you've kind of set up a normal addition process. All right. So the next slide here is high alkaline resistance. And so what this sealing process entails is usually a cold seal step on the front end, followed by a hydration step of some sort, or a second step seal on the back end, which can vary in terms of type of chemistry used. But the critical portion of this is the type of cold seal chemistry you're using and how that cold seal is managed. So earlier I mentioned the immersion time in a cold seal. When you're doing high alkaline resistance and you're trying to achieve a pH of 13.5 environments, this is a scenario in which your cold seal immersions may be longer than the 7 to 10 minutes we had mentioned earlier. Because the nature of the application, sometimes these cold seal steps can go up to 15 to 20 minutes and then be followed by a subsequent step that's another 15 to 20 minutes. But the intent here is of that total seal time being as much as 40 minutes is to create a part that when immersed in a bath of 13 and 13.5, which is essentially caustic, it doesn't strip or it can hold up to it. And so what you'll see here is in the image to the left, a part that has been immersed, half of it has been immersed and it was dyed black into a 13.5 pH solution. The part on the left did not have the correct fluoride additive or the proprietary additive in the second step. And as a result, you saw some significant color loss as it related to the black dyed part. The part on the right had the correct amount of fluoride additive in the component and also had the correct proprietary additive in the second step. And you'll see there's no visual difference in those panels. So again, the type of application for the part plays a role in this. So if you are going into a high alkaline resistance sealing environment, the margin of error is even lower. So managing these additives and ensuring that you are dialed into your chemistry is absolutely critical when you're doing something like this. All right, nickel-free sealing. So nickel-free sealing has become popular for the simple fact that managing nickel and disposing of nickel has become very challenging from an environmental perspective. The biggest challenge with nickel-free sealing is finding a nickel-free seal with the correct dispersing agent or surfactant that will also yield a good ADT and good seal quality. So what this slide shows or basically three different panels. One, no dispersing agent. The second one, the incorrect dispersing agent. And the final one, the correct dispersing agent. And much like the hot nickel and the mid-temp nickel, these dispersing agents break down over time. So it's very important that we find which one works the best. And when it does work, are there any risks of it having some sort of optical degradation in the field? And so one of the things that I always tell customers to look at when they're dealing with nickel-free sealing is when they're using a nickel-free seal, does the seal bath get cloudy over time? Does it get milky? If those types of things are happening, your surfactant may not be the correct one. And in fact, you may be creating more problems as it relates to smut because of that milkiness or that cloudiness in the seal getting onto your parts. The final thing to look at when you're looking at nickel-free sealing is when you assess whether a part is good, you need to look at it from the perspective of yellowing. So many nickel-free sealing applications involve clear or electrolytic that is used for architectural applications. And when exposed to UV light or extreme heat, certain surfactants or dispersing agents will yellow. And obviously, if this is going to be on the side of a building or a storefront, that is not an option. So it's absolutely critical to understand the type of surfactant you're using, the risk of potentially yellowing that could occur, because for the nature and the application of these non-nickel seal products, that cannot happen. And then kind of like you've seen in other slides, what you'll see at the ADT values here are, again, before the additive addition, after the additive addition, a significant drop in overall coating dissolution. Now, what I will say is before the additive was made with this non-nickel seal, you'll see that it was at 17.7 milligrams per square inch. That was higher than even the hot nickel seal. So based off of this data, as a rule, nickel sealing, because it uses nickel, will give you an improvement because it does filter UV light. So keep that in mind whenever you're selecting your seals. There is a benefit of nickel as it relates to operating margin and being able to have a poor seal, but by having nickel in the coating, regardless of whether it's a good or bad seal, you're going to get some benefit. All right. So I'll turn this over to Archana. She's going to go through kind of the seal quality testing and a few other aspects of sealing issues and light fastness.
Hi, so now that we know everything about different types of seals and the additives that are used for the seals, we'll look into the seal quality testings. So the seal quality checks are very critical in order to ensure that the parts produced by an anodizer meet the end application or requirements of the customer. There are several types of sealing tests that are performed to check the seal quality, as you can see in the table. The first one and the most widely accepted test is the acid dissolution test, where a part is immersed in a hot phosphoric chromic acid solution bath for a certain amount of time, and the weight of the part is noted before and after the immersion. This will tell us the amount of weight lost in the part, which will in return tell us the quality of the seal. Now, the second most popular test used in the industry is the modified dye stain test, which is done by using a certain strength of nitric acid and a blue dye. In this test, if a blue stain is appears on a part after the test, you know that the seal quality is poor. The third one is the high alkaline resistance test. In this particular test, a part is immersed in a solution of a high pH, which ranges between 12.5 to 13.5, usually 13 or 13.5 pH. This particular test is used in the automotive and cookware industries, where these parts, the cookware and the automotive parts, go through a lot of these rigorous solutions with high pH. The fourth one is the Clorox test, where we test the seal quality, where we test the effect of bleach on the seal. Now, the next three are used to test the corrosion resistance. The first one is the salt spray test, which is this test produces an accelerated corrosive attack on the coated sample, and which to evaluate the sustainability of the coating. And in this test, a salt water solution is atomized by means of a spray nozzle using pressurized air. The pH of this solution, the salt spray solution, generally is between 6.5 and 7.5. Now, There are variations of this test where other chemicals are added to this salt solution. One such solution is acetic acid with copper, which gets us to our next test known as the CAS test, or copper accelerated acetic acid salt spray test. The pH of this solution in ranges is usually between 3.1 to 3.3. And this test is done for the corrosion resistance for 24 to 48 hours. The last one is sulfur dioxide fog, which is used to mimic the acid rain. Now, from all these tests, the most widely used and the most reliable test and the accepted test is the acid dissolution test, which gives us a quantifiable number for the seal quality, whereas the modified dye stain test only gives us a pass or a fail of the seal quality. Now, we will look into the last light fastness with the seals. The first one is the non-nickel seal, where we used 3 different seals, a hot DI seal and 2 non-nickel seals. And the panels used for this test were produced using a high performance organic black dye. And you can see based on the results that the non-nickel seal did not really perform that well only after 5 hours of accelerated light fastness test. You can say that in general, the non-nickel sealing does not provide us with good results, especially with the organic dyeing. Next one is hot nickel seals. In this particular test, we used our mid-temperature seal with 2 different concentrations of nickel. And even in this test, the panels used were made with high performance organic black dye. So based on these pictures, you can see that hot nickel sealing performed way better than the non-nickel sealing. However, you can see the concentration of the nickel in the seal plays a really important role in the light fastness durability. So by looking at this, we can say that the more nickel that we can incorporate in the coating, the more light fastness a part will be. Coal seals. So we used 2 coal seals. One was a nickel coal seal and the other one was a non-nickel coal seal. And as usual, these parts were made with high performance organic black dye. And based on these pictures, you can see that the coal seal resulted in the best light fastness durability while using organic dyes. You can see that even after 24 hours of a light fastness accelerated test, the loss of color was very less as compared to a hot nickel seal, even at a concentration of 7% nickel content in the seal. Again, the amount of additive in this particular seal plays a lot plays an important role as the fluoride content in the seal is higher as the amount of nickel incorporated in this particular with this particular seal is 4 times higher than a hot temperature seal. Now we go on to the next slide, which deals with the sealing issues. And troubleshooting sealing smut can be a very challenging issue because it is caused by various parameters such as pH, additive concentration, temperature, precipitation of the salts, and rinse waters, alloy, and the chloride contamination either in the rinse waters or in the seal tanks. In many cases, smut is a bigger issue, especially for mid-temperature and high-temperature seals due to the use of the surfactant. This surfactant is used to reduce the surface tension in the coating. These chemicals, especially the mid-temperature and high-temperature seals, require a rigorous maintenance of the seal additives with the maintenance of the pH to ensure that the smut is eliminated. Residue and powder. Precipitates and other solid residues are usually visible at the end of the anodizing process, usually during the dyeing and the sealing processes. There are several factors that can cause the precipitates to occur. One of them is the nickel hydroxide of precipitate formation, surfactant drying from seal, algae residue from dye or rinse tanks. The nickel hydroxide formation is usually linked with the higher pH. If the pH of a seal of a particular seal goes above 6 pH, the nickel hydroxide precipitates and this particular thing cannot go back into the solution. You can see in the picture how a nickel hydroxide precipitate looks, and on the right you can see how a normal nickel seal looks. The next one is iridescence or rainbowing. This basically this iridescence and rainbowing is caused during sealing, and factors can be over-sealing as a result of extended immersion, excess of fluoride additive when cold sealing, incorrect seal additive concentration with mid-temperature and high-temp sealing, and incorrect seal or additive type used with mid-temperature or high-temp sealing. So it's not the use of the additives in a particular seal, one should be using the correct type of additive for a particular seal. You can see in the picture that with iridescence, there is even visible fingerprinting on the parts. Typically, the best way to manage this issue can be to reduce the seal timings or to ensure that the chemistry is being used at the recommended parameters. Now, the seal test failures. As mentioned before, the most common tests used in the industry is the acid dissolution test and the blue stain modified test. If you see the picture at the top, you can see two parts where a part failed the acid dissolution test and a part where it passed the acid dissolution test. The part on the left was sealed in a seal where it did not have the correct amount of additive in it, and the part on the right was went through the test after the content of the additive was modified. When testing seal quality, the most robust testing procedure, as I told you, is ADT, because it actually gives us the quantifiable number on how good or bad a particular seal is, whereas the modified dye stain test only tells us a pass or a fail of the test. You can see at the picture below for a modified blue stain test, once the concentration of the additive is changed, the panel passed the blue dye stain test. Now, the poor seal quality can be caused due to various parameters such as temperature variation of the seal, the pH of the seal, the concentration of the seal additive, the concentration of the nickel, and the usage of the correct seal, and the anodic coating parameters such as the density and the thickness of the seal. Now, it can happen that, for example, if you have two parts that have been processed on the same rack, but one of the part passed the dye stain test and the other one did not. In this place, we should use an acid dissolution test, which will actually tell us what the real reason is, because it could be that the density or the thickness of one particular part that did not pass the dye stain test had a lower coating density or the thickness. Since sealing is one of the most critical steps in preserving the anodic coating, the anodizers must understand all the factors that contribute to effective sealing. In most of the cases, managing of basic seal additives plays a crucial role in ensuring high quality sealing, particularly in case of light fastness. Along with the maintenance of the chemistry, the pH, and the concentration of the actual seal. If the seal additives are not correctly controlled, you can see issues like, for example, the one with the high fluoride content, you would see some iridescence, and for the cold seal or as well, if the fluoride content is less, you can see that the part may fail the blue dye stain test or the acid dissolution test. Yeah, and also when these additives are not controlled properly, other issues such as fingerprinting, dye bleed, white spotting, yellowing, and seal test failure can occur. This is very important that each type of seal chemistry has a unique seal additive that must be monitored. For the hot water, the smut suppressant, this suppressant stops the formation of smut associated with the sealing by reducing the hydration at the surface of the coating. For the hot or mid-temperature seal, the surfactant used in the seal is pretty important, which reduces the surface tension of the anodized part to ensure the active ingredient can enter the pore. For the cold seal or the room temperature seal, the fluoride content is pretty important to maintain, which ensures that the nickel can be incorporated or transported into the pore rapidly and efficiently. For the nickel-free seal, again, the surfactant is very important. And for the mid-temp seal, that is the nickel-free and uses surfactants to control smut. Now I'll give this to Tej if he wants to add some more pointers on this issue.
Yeah, no, I think the most important thing here is, depending on whatever seal chemistry an anodizer is using, they just need to be aware of the trade-offs associated with hot, cold, nickel-free, and realize that before they dump a bath, there may be still a way to salvage it. So the intent of this presentation is to arm you with some questions to ask yourself and to test with your seal bath to see if it in fact is salvageable. And perhaps, for depending on what application you need, high alkaline resistance, automotive, whatever it may be, maybe you need to change your seal chemistry to align with whatever that application is. But hopefully everyone finds this informative. If you have any questions, please don't hesitate to contact Archana or myself, or reach out to us via the website. Thank you.